Assalamu alaikum. We are going to continue with the topic of compaction. In our last class, we discussed about the standard Proctor test, and in the standard Proctor test, the purpose is to find out the maximum dry unit weight that we are going to get for a certain amount of water content, that is called the optimum water content. So, if you remember, we talked about this test. In this test, we perform this test at least 5 or 6 times. So when we plot the data, in the beginning the density is going to increase, and then after that the unit weight, the dry unit weight is going to decrease. On horizontal axis is always the water content, and the vertical axis is the dry unit weight. Okay, so when the dry unit weight is maximum, this is gamma d max, and then corresponding water content is called WOPT. OPT means optimum. Optimum means it's the water content that will give us the maximum density, the maximum dense state for a certain amount of energy that we are giving. So if you remember, when we studied this test in our last lecture, we take a standard mold. This mold is the diameter is 4 inches, and this mold has a volume of 1 by 30 cubic foot, or if we go in centimeter, then it is 943 centimeter cube. Okay, we place the soil in 3 layers. And on each layer we apply energy with the help of a hammer that is dropped from a height of 12 inches. Okay, so when the soil is compacted, we can find out what is the unit weight of this soil, and then we can find out the water content, and this test is repeated at least 5-6 times, and when we plot this data, we get this kind of curve. Okay, so one more thing is, we know that the dry unit weight is equal to this formula, GS gamma W over 1 plus E. We derived this formula in the chapter of phase relationship, and also the void ratio is E is equal to W GS over S. S is degree of saturation, small w is water content. So if I place this E value here, so then the equation is going to modify. Gamma D is going to be equal to GS gamma W over 1 plus, instead of E, now I'm going to write W GS by S. Now in this equation, the only thing that is going to change is water content and degree of saturation. Specific gravity of solids is constant for any material, and also the unit weight of water is also constant. So what we do is, we are going to make a table. Let's say this is our table. We are going to make a table, and we are going to get these values for different water contents. For example, suppose my water content is let's say 10%, 20, 30, 40, and so on, 50, and you can keep on increasing from, you can start from 5 and you can move on. And then we are going to get the, here I'm going to write gamma D, but this gamma D is going to be different for different degrees of saturation. So suppose my degree of saturation S is 60%, and then the degree of saturation next is 80%, and then degree of saturation is 100%. So what we do is, we are going to put in this formula the S value. For example, when S is 60%, S is going to be 0.6. So when S is 0.6, and we keep on changing this water content, this W, first it is going to be 0.1, then 0.2, then 0.3, then 0.4, then 0.5, and then we are going to get these values. And similarly, we repeat this for degree of saturation 80%. Then we repeat it for 100%. So we can plot all this data on this graph. So when we are going to plot this data, we are going to get these kind of curves. So it is going to look something like this. So this line is for 100% saturation. This line is, let's say, 80% saturation, and this line is 60% saturation. So this line of 100% saturation is also called the zero air void curve. Zero air void curve. Now what is zero air void curve? Zero air void means the air is zero, means there is no air. So whenever we say zero air void curve or ZAV, it means we are talking about saturation equal to 100%. So when the saturation is 100%, then this equation, we can call it gamma ZAV, is going to be equal to GS gamma W over 1 plus WGS. Now where is S? S will be 100%, means 1. So that S is going to not appear here in this equation. That is 1. So when we multiply it with 1, so there's no change. So this is called the zero air void unit weight. So this value is corresponding to this curve. So nothing is going to plot beyond this, because if you go beyond this, the saturation is going to be more than 100%, which is not possible. Saturation can only be 100%. Okay, so let's now discuss the effect of energy on the compaction. So in our last class, we talked about standard Proctor test. Now, what is standard Proctor test? In standard Proctor test, we use a standard hammer of weight 5.5 pound. So the standard Proctor test, the weight of hammer is 5.5 pounds. So if you convert into kilograms, it is going to be 2.5. Okay, and the height of drop, the drop of this hammer is 12 inches. 12 inches, or I can say 1 foot. And the total number of drops, okay, so let me write here it is drop height. And the number of drops are going to be 25. And then the number of layers that we place in the mold, number of layers, these are the number of layers that are compacted, that are going to be 3. So it means the soil is placed in 3 layers, and each layer is compacted 25 times, and every time the hammer is dropped by 1 foot, and this is not 1 inch, it is 1 foot. 1 foot, and the weight of hammer is 5.5 pounds. So the energy that we are going to apply to this sample is going to be, and remember this energy is the energy per unit volume. So energy is going to be equal to, so the hammer is 5.5 pounds and it is dropped by 1 foot. Okay, when this drop is one time, it is 1 foot times 5.5, and this hammer is dropped 25 times, and this thing is applied 3 times. Okay, so this is going to be pound foot. So pound is this weight that is dropped by 1 foot. So when this is dropped almost 75 times, this is going to be the energy, and we have to divide it by the total volume. So the volume is 1 by 30 cubic foot. So when we simplify this, this should come as 12,375 pound-foot. So this is the energy that uh, we transfer when we are using the standard uh, Proctor test. Now, the second test is called modified test. Okay, what is modified test? Modified Proctor test. So in modified Proctor test, we are going to use a hammer of okay, I think it's 10 pounds. Yes, it is 10 pounds. So the hammer is 10 pounds. The drop height of this hammer is 18 inches. So 18 inches means if you divide it with 12, it is going to be 1.5 foot. And the number of drops on each layer is same as 25, but this time we are going to compact it in 5 layers. Number of layers are not 3, but it is going to be 5. Let's look at what is the energy. So energy is going to be the hammer is 10 pounds, the drop height is 1.5 foot. This is the energy that is transferred in one drop, and we are going to drop 25 times, and there are going to be 5 layers, means the total drops are going to be 125, and we should be dividing it with the volume. So actually here it was pounds, and then in bottom was cubic foot. So on the top is pound and in bottom is 124 cubic foot. So when we simplify this, we are going to get 56,250 pound foot per cubic foot, because we are talking about unit volume. This is pound foot per cubic foot. Okay, because here, okay, let me correct it here. This 10 is this pound and 1.5 is this foot. So this total is going to be, this is going to be pound foot. And similarly here we have 5.5 pounds and the drop is 1 foot. So total is 75 times. So this is going to be also pound foot. So the total volume is pound foot per cubic foot. Pound foot per cubic foot. Okay, so this is our, these are our units and these are the values. So we see that we give more energy in modified Proctor test. So in modified Proctor test, the energy is 56,250 and standard is 12,375. So what is the ratio? So we can find out the ratio, how much energy we are transferring in modified, how much more. It is 56,250 divided by 12,375. So if you divide this, it will come around approximately 4.5. It means we are giving 4.5 times more energy in a modified Proctor test. So 4.5 times more energy is transferred to soil in modified test as, okay, I don't have space here, as compared to standard test. Okay, let me copy this from here because it's not clear here. So let's copy this So we can say that when we are using modified test, we are giving 4.5 times more energy. 4.5 times more energy is being transferred to the soil. 4.5 times. This is important. 4.5 times more energy. So it means when we are giving 4.5 times more energy, we are going to definitely have more density. So let's look at the comparison. So here is a soil that was tested 1, 2, 3, 4, 5, 6. 6 times this test was performed, and when we connect these points, it's a bell shape. This is the bell shape that we get. So this is the peak value. This is the maximum value. So this is that maximum value. It's almost 1.72 something. And when we are going to compact the same soil with the modified test, we provide 4.5 times more energy. Then in that case, the maximum density that we achieve is going to be close to 1.88 something. And if we look at the water content, in case of standard test, water content was somewhere 17%, and in case of the modified test, this becomes 13%. So you see, when we give more energy, we will get more density, and that will be achieved at less water content. So if we connect these points of peaks, if we connect these peaks, so we get this kind of line. And if you see, this line is running parallel to these curves. This is the curve for 100% saturation, 80%, and 60%. So this is called the line of optimum. So it means if we keep on increasing the energy, we are going to having we will get more density at less water content. Okay. So this is the another diagram from another book. What we did is we take a soil whose specific gravity of solid is 2.7. Okay, it's a sandy clay. Liquid limit is 31 and plastic limit is 26. So when we give 20 blows per layer, so we get this curve, and then we keep on increasing the energy. 25 blows per layer, 30 blows per layer, and 50 blows per layer. So what is happening as we increase the energy? As we increase the energy, the maximum density is increasing, and the optimum water content is decreasing. There's a increase in, so there is a increase in gamma D, and there is decrease in the optimum water content. Okay, and this is the line of optimums. So this is the effect of energy on the uh, on the density. Okay, so these are typical shapes that we are going to see in some of the soils. Most of the time we are going to get this bell shape. Most of the time we are going to get this bell shape. But there are some situations where we might have more than one peak, one and a half, like CBC. There's a double peak here. There's one big peak and there's a small peak. We will sometimes initially when we compact, it will start showing decrease in the density, and then it might show some increase in the density. So these are possibilities, but most of time we are going to get this kind of shape. Now there are some problems related to the compaction. So let's look at these problems. Okay, here is our first example of this chapter. The problem is that a soil sample was taken from a site, and that site where we are going to take soil, that normally is called borrow area or borrow pit. Borrow pit is Borrow area is the area from where we are going to take soil, and we are going to use this soil in the construction. Either it is going to be used in road construction, or it is going to be used in dam construction. Anyway, whatever is the project, we take soil from the area, we bring it to our lab, and then we perform the standard Proctor test. So this test was performed 5 times, and every time we got the dry unit weight and the water content. So these are 5 values, and from here what is required is we are going to get what is the maximum dry unit weight. We are going to determine what is gamma D maximum and what is the optimum water content. So this is what is required, and once we get these two values, we will try to compact the soil in the field with reference to these values. So we will try to achieve these values in the field. So this is the reference values. Okay, and then on the same data, we are going to do another example. The next example says, from this test we are going to compact the soil to 95% of this maximum dry unit weight. We are not going to achieve 100% compaction. We are going to try to achieve 95% of the compaction. In that case, if we are going to attain 95% of the compaction, or 95% of the dry unit weight, then what should be the range of water content? So these two examples are based on this same data, So let's start with our example. So the same data I have written here in the column, the water content and dry unit weight. So here's our graph. So let's plot this data. So the first value is water content is 9.1% and dry unit weight is 107. So 9, so we draw a vertical line here, and 107. So this is our first point. So this is the first point, this one. The second data is 11.8 and 109.8. So 11.8 is means it's very close to 12, so it's close to 12, and 109.8. So I can round off this 109.8. I can say that this is actually 110. So this is 109, 110, 111. So that is 110. So this is the point. This is the second point. Okay, next is 14 and 112. So this is 14 and 112. So this is 111 and this is 112. So this is that point. Third one. The fourth point is 16.5 and 111.6. So this is 15, 16, 17. So this should be 16.5. So this is 16.5. So we draw a vertical line from 16.5 and then 111.6. This is 111, 112. So 111.6 is going to be somewhere here in the middle. So this is our point. And the last point is 18.9. So this is 18.9. I can round off to 19. So this is 15, 16, 17, 18, and this is 19. So we draw a vertical line from 19 and 107.3. This is, remember, 108. This is 107.5. So this should be 107.3. So that is the point. So we are going to now combine all these points with the help of a curve. So when you are doing this, you should be doing it with first pencil. So try to make it as smooth as possible, and if the curve is not good, you should rework. So if you plot this in Excel, it is going to give you very smooth bell-shaped curve, and it is going to be more accurate. So now I can make it dark. So this is our bell shape. Now from here we can easily find out what is the maximum unit weight. So suppose this is the maximum, so draw a horizontal line. So this is that maximum. So this maximum is little bit above 112. So even I can maybe take 112, or I can say this is 112 point, if this is 112.5, maybe 112.2. Okay, this is pound per cubic foot. So I can say that gamma d maximum is 112.2 pound per cubic foot. And what is the optimum water content? And from there draw a vertical line down. So it's very close to 15%. So I can say optimum water content is going to be maybe 14 point. Remember, this is 11, 12, 13, 14. So this is almost 14.9%. So this is what we get from here: the maximum dry unit weight and optimum water content. Now this is the maximum density that we got in the lab. Remember, in lab when we are compacting, it's very small mold and it's very controlled environment. But when we are going to compact this soil in field, there are so many uncertainties, there are so many factors. So we may not be able to achieve 100% density. So mostly we are going to achieve some percentage of this. Let's say 95%, 98%, 97%, 90%, 80%, whatever. It depends on the design of the project. So the second part of question says, using the results of the standard property test given in this previous problem, determine the range of water content most likely to attain 95% or more of the dry unit weight. Means we are going to attain 95% of this density. So what is the 95% of this density? So let's look at it. Let me insert one slide here. So the dry unit weight that we attained, gamma d max, we got it 112.2 pound per cubic foot, and we want to achieve 95% compaction. So there's a formula here, percent compaction. Now what is percent compaction? How much you achieve in the field. So it is gamma d in the field and gamma d maximum that we attain in the lab, and then we express it as a percentage, right? So in this question says that the percent compaction is 95%. So what gamma d we are going to achieve in the field? Gamma d field is going to be equal to 0.95. 95% means 0.95 times gamma d maximum, and gamma d maximum is 112.2. So if we multiply this 112.2, 112.2 times 0.95, it is going to be 106.6, 106.6, or I can round off to 107 pound per cubic foot. So we will try to achieve 107 pounds per cubic foot in the field. Now where is 107 pounds per cubic foot? So you see our curve starts at 107 and the curve finishes here. So what we can do is we can extend with the same slope, with the same trend. So now let's look at where is 107. So this is 100% compaction and 95% compaction is 107. So I can write here, this is 100% compaction and this is 95% compaction. Okay, 100% is 112 and 95% is 107. So when you look at 107, so at 107 there are now two water contents. So 107 is at this water content and 107 is at this water content. So there are two possibilities. So it means we have got this range. This is all the range of water contents if we want to attain 95% compaction. For 95% compaction, if your water content is between 9 and let's say, what is this value, 19 point something, so this has to be from 9 to 19.5%. so this is the water content range. Okay, so I can summarize here. For 95% field compaction, for 95% field compaction, what is the water content range? Okay, instead of W, let me write water content. The water content range is from 9 to 19.5%. So if the water content in the field is anything between 9 and 19.5, means if it is 10 or 11 or 12, if it is in between these two ranges, we can attain the compaction of 95%. So just remember, and this is very simple, just remember that percent compaction is gamma d of field, what we attain in the field, and then gamma d maximum, what we attain in the lab. And this lab value is what we call it our reference value. So it means this test is performed so many times when we are working on a road project or whenever we are working on a dam project. So whenever we are going to select a soil for use in the project, we are going to bring that soil, we are going to bring it into the lab, and we are going to find out the gamma D max and optimum water content, and that will help us in achieving compaction in the field. So there's another question here. The question says, a soil sample was taken from a proposed cut area in a highway construction project, and it was sent to a soil lab for a compaction test, and we used a standard Proctor test. Okay, a standard Proctor test was used on that soil sample, and from the test we got maximum dry unit weight of 112.6 pounds per cubic foot and optimum water content of 15.5. So this is gamma D max, okay, and this is W optimum. Now the contractor during the construction of the soil embankment achieved the following. So this is gamma D of the field. The question is percentage compaction. What is the percentage compaction? Now it's just one line problem. Percent compaction is gamma D of the field, or the dry unit weight of the field, and the dry unit weight of the lab maximum, and we express it as a percentage. So it means if we put the values, it is going to be, in the field we got 107.1 and in the lab it was 112.6 multiplied by 100. So let's multiply 107.1 divided by 112.6 times 100. So it will give us 95.11%. So the contractor was able to achieve 95% compaction during that process. Okay. Now let's look at another example, and the example says a test was performed in the lab. A standard Proctor test was performed in the lab, and the mold that we used is standard mold. The volume of mold is 1 by 30 cubic foot. The mold's weight is 4.35 pounds, and the combined weight of mold and the specimen compacted is 8.63. So the weight of soil plus mold is 8.63, weight of mold is 4.35, volume is given, and the water content of specimen is 10%. So what we have to do, we have to find out gamma D, we have to find gamma, and we have to find gamma D. Now this question is very simple. Remember, we have mold, and remember this mold is 4.35 pounds. Now I can say that the weight of soil plus mold is 8.63 pounds, and the weight of mold is 4.35. So what will be the weight of soil? The weight of soil is going to be, we have to subtract, we have to remove this weight of mold. So 8.63 minus 4.35, it will give us 4.28 pounds. So the weight of soil during compaction was 4.28. So how can I find out the volume? The volume is given 1 by 30 cubic foot. So weight is 4.28 pounds, and the volume is 1 by 30 cubic foot. So what will be the unit weight? Gamma is W over V. So it is going to be 4.28 divided by 1 by 30. So this is pound and this is cubic foot. So this will give us 128.4 pound per cubic foot. Okay, so we got gamma as 128.4 pound per cubic foot, and the water content is given as 10%. So from there we can get gamma D. Remember, we derived this formula in our previous lectures. Gamma D is gamma over 1 plus W. So gamma D is 128.4, 1 plus, and remember we never put it as a percentage, so it is going to be 0.1, 1 plus 0.1. So this is going to be 116.73 pound per cubic foot. So from this test, gamma comes as 128.4. So instead of writing pounds per cubic foot, sometimes we write ECF. ECF is same, pounds per cubic foot. This is the short for writing pound per cubic foot, and gamma D is 116.73 ECF. So this is the result of that test. Okay, now let's develop some formulas that we are going to need in some more kind of problems that we are going to deal in coming lectures. So I'm just going to develop those formulas. We will be talking about, there are two terms that we are going to be talking about. One is called borrow area. This is called borrow area, or sometimes we call it borrow pit, same thing. Okay, and then the other is fill area. What is borrow area? It's a natural area where we are going to excavate the soil. We are going to excavate the soil using different machine. We are going to put it in trucks. Okay, we are going to fill this into the trucks, and these trucks are going to transport it to the construction site. On the construction site, we are going to place it in the in the fill. This is called embankment. This is called fill embankment. Fill embankment. So anyway, there are two kind of areas. One is called borrow area, and number two is called fill area. So the void ratio of this borrow area will be called as E sub B, and the void ratio of fill is going to be called E sub fill, and the unit weight, dry unit weight of the borrow area is going to be dry unit weight sub B, and then dry unit weight of the fill. And also we are going to use the volume of borrow area and also the volume of fill. So these are the basic terminologies. We excavate soil, we put it in trucks, and those trucks are going to bring the soil, and then we are going to use different machines to compact, and the soil is placed in layers. So in thin layers we place the soil and we keep on compacting with different machines, and we keep on rising till we reach our desired height. Okay, and we are going to see in coming lectures what are the equipments that we use for compaction. So let's look at the formulas. Now, one basic thing is, whenever we are going to excavate the soil, it will get disturbed, and the density is going to change, and even the void ratio is going to change. So void ratio of the soil from excavation, from borrow area, and the void ratio of the fill is going to be different. The moisture levels are going to be different, because when you are excavating the soil, we put in the trucks and we are bringing it to the fill area, water may evaporate, or if it is raining on that day, maybe the water is going to add. So the wet unit weight is not constant, it is going to vary in the borrow area and in the fill. And also when in the fill, we are going to compact it by adding water, so we cannot use this as a reference. So what is constant in these two is the weight of solids. So whatever soil we excavate here, it will consist of weight of solids plus weight of water, but that weight of water is going to vary. But what is not going to vary is the weight of solids. So weight of solids of the fill area is going to be same as the weight of solids of the borrow area. This is important point. So weight of solids of the borrow area should be same as weight of solids of the fill area, but we cannot say this for the weight of water. Water weight is going to change during the transportation. So from here I can develop one formula. It's very simple. We know that the formula for gamma d is weight of solids over volume. So from here I can write weight of solids is equal to gamma d times v. So it means this formula is going to get modified. So instead of weight of solids, I can write gamma d, gamma d times v. So instead of ws, I will write gamma d times v, and here is borrow area. Should be equal to gamma d times v of the fill. So I can write dry unit weight of borrow area times volume of borrow area should be equal to dry unit weight of the fill times the total volume of the fill. So this is one formula that we are going to use in our coming examples. There is another formula. Okay, let's look at it. The second formula is, we are going to start from the same. Weight of solids of the borrow area should be equal to the weight of solids of fill. So we know that, here let me develop the formula. We know that gamma d is gs gamma w over 1 plus e, right? This is the relationship we used earlier also. Now what is the formula for gamma d? Gamma d is weight of solids over total volume. It should be equal to gs gamma w over 1 plus e. So if I bring this volume on the other side, weight of solids is going to be equal to gs gamma w total volume over 1 plus e. So let's now replace this. So weight of solids is going to be equal to Gs gamma W volume over 1 plus E for baro should be equal to Gs gamma W volume over 1 plus E for fill. Now, whether you are in baro area or you are in fill, the gravity, specific gravity of solid is going to remain same. It's a constant quantity. Okay. So, and also the unit weight of water is also constant quantity. It's not going to change. So we are going to take out those constants. So Gs gamma W will come out. So it is going to be volume of baro area divided by 1 plus, I can write instead of outside B, I can write it like this. And here let's take this common Gs gamma W. It is going to be volume of fill over 1 plus E fill. So on both sides they are going to cancel out. So what is left? Volume of baro divided by 1 plus void ratio of the baro area should be the volume of fill over 1 plus void ratio of the fill. So these are the two formulas that we are going to be using in our coming examples. So they are very simple. If you forget, you can very quickly derive this. This is one formula, and this is the second one. This one. So I think this is enough for today's class. So in my next class, I'm going to use these two formulas to solve some further problems that are related to compaction in the field. So please, when you watch these videos, do make your lecture notes. Thank you so much and have a nice day.